Hello and welcome to this revision session for AQA A-Level Physics Paper 1. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 1. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics to understand what topics we need to improve upon for AQA A-Level Physics. So when carrying out this revision session, you should divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? So the first step is to learn the key facts. So use the revision guides, class workbooks, student prep notes, textbooks to learn the key ideas of the course. And you might wish to make mind maps or write out notes yourself. The second step should be to test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and this could be done from your own cue cards. And then finally, the third step is to practice examination questions using things like exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and mark your own work, and you may wish to download your own examination papers to help do this. So the three steps of learn the key facts, then testing yourself and then practicing exam style questions are how you should be revising AQA A-Level Physics. So let's now practice some questions for AQA A-Level Physics Paper 1. So the first topic is particles and radiation. So answer the following question. Electrons and positrons each have a rest energy of 0.511 MeV. State what is meant by rest energy. In figure 1 shows an electron and positron travelling towards each other just before they collide. Each particle has a kinetic energy of 0.340 MeV at the point of collision. Describe with reference to the energies involved the outcome of the collision. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, you've got to firstly know what the definition of rest energy is in terms of particles. So rest energy is the energy equivalent of the mass of the particle when it's stationary or when it has a kinetic energy of 0. Now for the second question, you've got to consider the information AQA have given you in the question. They've mentioned it's an electron and it's a positron, so therefore they are the particle and antiparticle pair. So it's asking you what will be happening when a particle and antiparticle collide with each other. In addition, it's give you the kinetic energy and the rest energy of the particles, so you can refer to that in your answer as well. So you'll know that the electron and positron will annihilate as they're a particle-antiparticle pair. They'll produce two gamma photons, producing two photons to conserve momentum as they're traveling in opposite directions, and the total energy of each will be the kinetic energy plus the rest energy, which will be 0.851 MeV. So the next question says, a beta minus particle is emitted when a nucleus of strontium-90 decays into a nucleus of yttrium. Firstly, explain the origin of the beta minus particle, then state the values of A and Z for the yttrium nucleus, and then third, in early studies of beta decay, the kinetic energies of the beta minus particle were measured. Explain how these measurements improved our understanding of what happens in beta decay. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first question is asking you fundamentally what is going on in beta decay. Now you've got to remember that beta decay takes place in the nucleus, so it's when a neutron in the nucleus will decay to form a proton, an electron and an antineutrino. So you'll need to be aware of what the beta decay process is. Now you should hopefully as well notice what happens to the value of A and Z in the beta decay. So A stays a constant value and Z will go up by 1, so the answers are 90 and 39. That's the same for all beta minus decays. And thirdly, it's asking you why the kinetic energies of the beta minus particles were not going to be constant. Well, they're not constant, and there's a range of kinetic energies up to a maximum because there's something else released in the decay along with the beta minus particle, because whilst the total energy is constant, it's shared over multiple particles. So that showed us we had to hypothesize the idea of the neutrino, and it actually found related to be the antineutrino to conserve lepton number was also produced in the decay process. The next question says, the following equation applies to the photoelectric effect. State what is meant and what is represented by the terms HF and EK max, and state and explain what is represented by the term phi. So pause the video now, then unpause the video when you want to go through your answer. So to answer this question, it's really important that you understand what each term means in the photoelectric effect equation. So HF links into the energy of the photon itself, whilst the EK max refers to the maximum kinetic energy of the electron emitted in the photoelectric effect. It's very important that you've got to remember what is the photon and what is the electron emitted from the absorption of the photon in the photoelectric effect. Now for this next one, you've got to understand that phi is the work function. That's a fact you've just got to remember, and it is the minimum, and you've got to remember, you've got to put the word minimum in there, energy required to remove an electron from the surface of the metal. Not just the metal itself, but the surface as well. Now in the following question, it says figure 6 shows a circuit used to investigate the photoelectric effect. The ammeter can measure very small currents. Monochromatic red light is instant on the metal surface of the cathode, and the current in the ammeter is 0. The red light is replaced with monochromatic blue light, and there's a current in the ammeter. Firstly, explain why there's a current with blue light but not red light, and then the intensity of the monochromatic blue light is increased and the experiment is repeated. State and explain any change in the current. So pause the video now, then unpause the video when you want to go through your answer. So when you're answering this question, you've got to always remember, what does the colour or frequency show you in the photoelectric effect, and what does the intensity show you in the photoelectric effect? Well, you've got to remember that colour or frequency links into the energy of the photon, which is required to liberate the electron. So the blue light photon is going to have more energy than the red light photon, because the blue light has a higher frequency. So therefore E equals HF. If F is higher and H is a constant, well therefore blue light photons will have more energy than red light photons. So that then tells you that there's enough energy above the work function for the blue light, but the red light photon has energy below the work function, so cannot allow the electron to be liberated. Now in the next question, you've got to always remember that intensity is how many photons hit the surface every single second. But it's always important to note in the photoelectric effect equation and in the photoelectric effect itself that one photon is instant with one electron. There's a one-to-one relationship between photons and electrons. That's a very, very common marking point for photoelectric effect equations. So therefore, if there's more photons every second and one photon interacts with one electron, that tells us that more electrons are going to have photons absorbing into them, so more electrons are ejected and therefore the current will go up. The next question says a sigma plus particle and an unidentified particle Y are produced by the strong interaction between a positive pion and a proton. The interaction is represented by the following equation. Complete table 1 to show the baryon number B, charge Q and strangeness S for the particles in this interaction, in which particle in table 1 has the quark structure UUS. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is all about what the different properties of the particles are. So you'll notice that with a proton, a proton will have a baryon number of 1. That's a fact you've got to remember. Whilst a pion, because you know that it's going to be a meson, will have a baryon number of 0. So if it's 0 and 1 before, if baryon number before equals baryon number after, that tells us that sigma plus also has to have a baryon number of 1. Now you know the charge of the pion plus is +1, of a proton is +1. Of sigma plus it's +1, so Y must also be +1 for the charge to be 2 before and 2 afterwards. Now you know that both the pion and the proton are not strange particles, because we know the only strange meson is going to be a kaon, and we know the proton from its structure itself is not going to be strange, so that's 0 and 0, so therefore the sigma plus has to be -1 for the strangeness to be 0 before and 0 after. Now you'll note in the question it tells you it's a strong interaction. interaction. So in strong interaction, strangeness has to be conserved. Now in the next one, which has the quark structure UUS, well, you know, if it's got 3 quarks in there, it's got to be a baryon, so therefore it can't be pi plus because we know that that is a meson. We know it can't be Y because that has a baryon number of 0, so it can't be a baryon. So there's only 2 options. You've got the proton and you've then got sigma plus. Now there's 2 ways you can think of doing this. Either you know what the proton structure is, which is up up down, or you can look at the fact that sigma is already indicated to have a non-zero strangeness, so that must have a quark structure with a strange quark in it. So the answer is sigma plus. The next question says, deduce with which particle pi plus or Y has the greater charge to mass ratio and justify your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, you can tell firstly that Y has a greater rest energy than pi plus. And why is that? Because we can tell from our previous question that pi plus and Y had the same charge because they both identify as having a charge of +1 from the previous question. Now you know that Y is going to have to be a kaon. Why is that? Because it has a non-zero strangeness and it has a baryon number of 0, so it's a strange meson, so therefore it must be a kaon. So therefore we can tell that pi plus has the greater charge to mass ratio because it has the same charge as Y but will have less mass, because we know that if it's pi it will be made up of up and down quarks which have less mass than the equivalent strange quark. So therefore what pi plus will have a greater specific charge, which is the charge to mass ratio. We will now be looking at questions to do with waves in physics paper 1. The following question says, a screen is placed 3 meters from a diffraction grating as shown in figure 10. The screen and the grating are parallel. Monochromatic light of wavelength 540 nanometers is incident normally on the diffraction grating. The central maximum appears on the screen at O. The first order and second order maxima on each side of O are seen at positions A, B, C and D. The distance between A and D is 1.32 meters, so that the angle between the 2 second order maxima is approximately 25 degrees. Calculate the number of lines per millimeter on the grating. The instant light is now replaced with monochromatic light of a different wavelength. More maxima are observed on the screen. State and explain any other change in the appearance of the pattern on the screen. So pause the video now, then unpause the video when you want to go through your answer. So in this question, what you firstly got to consider is the triangle that is produced between the parts of A, D and the part where the monochromatic light goes in. So what you should be doing is drawing a triangle in. It's always a really good idea that when you're looking at diffraction gratings and have a diagram like this, that you can draw in your right angle triangle, you can then work out your angle via SOHCAHTOA. So what you'll see is straight away that you'll have the opposite and you'll have the adjacent because they're clearly labelled in the diagram there. And then what that does is that then allows you to then work out what your angle is going to be. Now remember, the right angle triangle will go from where the monochromatic light is to O to A. So if you want the angle from A to D, you're going to have to double the angle that you are working out there, which is why the answer has been doubled. The next one, you've got to use the equation d sine theta equals n lambda. Now you've always got to remember as well, whilst it's not given to you in your examination, that the number of lines per meter is equal to 1 over d. So what you would do is you pop in your values, and again remember you've just worked out the angle from O to A, which is going to be 12.4. You know what your value of n is because you told it is the second order that it goes to, and you have your wavelength is 540 times 10 to the minus 9. Remember, nanometers is times 10 to the minus 9. You can then use that to work out your value of d, and then work out the lines per meter by doing 1 over d. Then you've got to convert it into millimeters because it is lines per millimeter, so you should get your answer of around about 200. Now the last question really wants you to think about what the pattern on the screen is going to be. So if you think about the fact that there are more maxima observed on the screen, the angle you are going to be working out in your equation d sine theta equals n lambda is going to be smaller because there are more orders on the particular screen, so therefore the angle is lower. So because you got your angle lower, that tells you that there's going to be a shorter wavelength because d sine theta equals n lambda, so it has a shorter wavelength. It'll appear bluer than it did before. If you look at the next question, it says figure 1 shows sunglasses that have a polarizing lens. The sunglasses are sold with a separate small polarizing filter. State and explain how the filter can be used to check that the lenses are polarizing. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this particular question, it's fundamentally asking you how do you test whether lenses are polarizing, and there's a standard experiment you can do. So you hold your two Polaroids, so in this case the sunglasses and the polarizing filter, rotate one about the other from 360 degrees. Now you should see that if it is polarizing, that there should be a change to the intensity of the radiation that can go through the two Polaroids. Now if they are completely aligned, so at 0, 180, 360, they should all go through, so should be the maximum brightness, and when they're at 180 or 270, in 90 or 270, my apologies, they're at right angles to each other, so nothing should be able to get through, and you get a minimum of radiation going through. The next question says the critical angle for light travelling from diamond to air is 24 degrees. The critical angle for light travelling from glass to air is 42 degrees. Explain what can be deduced about the relative values of the refractive index of diamond and the refractive index of glass. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is all about using the equations that you were given on your equation sheet. So you should see on your equation sheet that sine critical angle is equal to 1 over n. So we can tell at this point that if the critical angle is equal to 1 over n, or sine critical angle is equal to 1 over n, that diamond must therefore have a much larger refractive index than glass because the critical angle is much lower. The next question says, a satellite system is used to measure the height h of the top of an ice sheet above the surface of the ocean. The satellite emits two pulses, A and B, of infrared radiation. A is incident on the surface of the ocean and B is incident on the top of the ice sheet as shown in figure 2. Firstly, the frequency of infrared radiation is 3.8 times 10 to the 14 Hz. Each pulse has a duration of 6 nanoseconds. Calculate the number of cycles in each pulse, and then A and B reflect and return to the satellite. The travel time is the time between the emission of a pulse and its return to the satellite. The difference in the travel times of A and B is 10.7 microseconds. Calculate h. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one, what you've got to do, in your first question, you've got the frequency and you need to work out the number of cycles in each pulse. So we know that frequency is 1 over time period. So therefore we can work out what our time period is going to be quite easily. Time period is 1 over frequency, so therefore it works out to be 2.63 times 10 to the 15 seconds. Then we know, if you look on the previous question, that each pulse is 6 times 10 to the minus 9 seconds. So therefore you can work out the number of waves by doing 6 times 10 to the minus 9 divided by the time that we've just worked out to get 2.3 times 10 to the 6 waves every single second. 2.6 cycles in the pulse, sorry. Now the next question, what you're going to have to do is, because it's reflecting, we're going to be doing the equation speed is equal to distance over time. Now we know what the speed is going to be because we know, if we read the question here, it says infrared radiation. So we know infrared radiation has a speed of 3 times 10 to the 8 meters per second because it's an electromagnetic wave. Then we can work out what our time is going to be, because we can say for that time is distance over speed. Okay, and then we can work it through like that. We're going to work out the distance, don't we? So we can then work out what our time is going to be by doing 10.7 times 10 to the minus 6 over 2 to get our time period to be 5.35 times 10 to the minus 6 seconds. So we pop that into our equation where distance is equal to speed times by time, and we get 1.6 times 10 to the 3 meters. Now note, why have we halved the time? Well, because we've measured the time it takes the pulse to go there and back. So if we're trying to work out the distance to there, we're going to have to halve the time because we only want the time to there. The next question says, some of the infrared radiation enters the ice sheet. Figure 3 shows the path of infrared radiation that refracts at the sloping part of the ice sheet. Calculate the refractive index of the ice, then calculate the wavelength of the infrared radiation when it is inside the ice shield. Right, so how do you answer this particular question? Well, if you look on this question, you're going to have to use the equation n1 sine theta 1 is equal to n2 sine theta 2, and you pop in your values and you work it out to be 1.3 for your refractive index. Now note, it's very important that the angles are always taken from the normal, so you wouldn't be using 38 in this particular question because it's not from the normal. We would do a 90 minus 38 when we're trying to work it through. Remember that the refractive index of air, which we'll call n1, 1 is going to equal 1 in this question as well, so therefore we can use that to work out what the refractive index of the ice will be. So then how do you calculate the wavelength of this? Well, then we can say n equals c over cs, and then we can work out what c is going to be by doing c equals f lambda. So therefore you've got your frequency, you've got your wavelength. Okay, so at that point you can then work out what your speed is going to be by doing one over the other, and then you can work out your answer to be 2.3 times 10 to the 8 meters per second. We're now going to look at questions involving mechanics and materials. So in this first question it says figure 3 shows a stack of plates in a plate holder used in a hotel kitchen. The stack of 13 plates is supported by a spring. The spring is compressed by 16.7 centimeters when there are 13 plates in the stack. Each plate has a mass of 0.61 kilograms. The spring obeys Hooke's law when supporting 13 plates, and the masses of the base and the spring are negligible. So calculate the stiffness of the spring. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this through? Well, stiffness is another phrase for spring constant. So you look on your equation sheet and you see that F equals K delta L, so the extension. Now we also know that the force in this case is going to be the weight of the plates. So we can do F equals mg. Now we know that there are 13 plates here, so it's going to be 13 times by 0.61 times by 9.81 to get your weight. We can then say F equals K delta L, so therefore K equals F over delta L. Now remember, delta L is going to have to be in meters, so it's going to have to be 16.7 centimeters in meters, so 16.7 times 10 to the minus 2, and you work out your answer to be 470 newtons per meter. The next question says calculate the energy stored in the spring when there are 13 plates in the holder. Then when a plate is added, the spring compresses so that the base moves downwards by a distance equivalent to the thickness of one plate. This ensures that the top plate is always above the surface of the holder. Over time the spring becomes weaker and its stiffness decreases. Explain how the behaviour of the plate holder will be affected by the decrease in the stiffness of the spring. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this question you need to look on your equation sheet and you see E is equal to half F delta L, or you could do a half K delta L squared. Now we know what F is, it's going to be our weight again, so we've got our weight from our previous question. We've got delta L, remember again we work in meters, we pop them in there and we get 6.5 joules. Now in this next question it's very important you don't just give general facts about physics, but rather you answer the particular situation and scenario given in the question. So what you'll notice is that if we have a decrease in the stiffness of the spring, well that tells us that the spring constant or stiffness is the force needed to extend it by 1 meter. So therefore you would need less force to extend it by 1 meter. So this tells us that the plate was compressed more because you don't need as much force to compress or extend the spring. So to link it into the question asks the plates will now be well below the top of the well, so it'll be unlikely to see them. The next question says a falcon is a bird of prey that catches other small birds in flight. The falcon dives to increase its speed. Its gravitational potential energy decreases by 1,900 joules during the dive. The mass of the falcon is 1.1 kilograms. Calculate the vertical distance moved by the falcon as it dives. Then the initial vertical speed of the falcon is 25 meters per second. During the dive, the falcon's wings applies a vertical force downwards, transferring 1,400 joules of work. Calculate the maximum theoretical speed that the falcon could achieve in this dive. Then in practice the falcon will need to transfer more than 1,400 joules of work to achieve this maximum theoretical speed. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you know you're given the energy here. Now again, you're not given enough information to use SUVAT, so you've got to use the energy stores in this situation. You're told the gravitational potential energy change, and we're trying to work out H, or the vertical height difference. So EP equals mgh, work it through and you get 176 meters or 180 meters to two significant figures. Now in this next question again, you don't have enough information to use SUVAT, so you've got to use the changes in energy store. So you'll notice that when it's starting, it has an initial speed, so it has an initial kinetic energy, and then it will also have work being done on it, and it will also have gravitational potential energy as it is high up. Now the maximum theoretical speed is when all these energy stores will go into into the kinetic energy store, and you can then use that to work out the speed of the object. So you can work out your initial kinetic energy with a half mv squared, add it to the work done, which is given in the question, and the gravitational potential energy, equate that to the final kinetic energy, and then work out v from the equation. Kinetic energy equals a half mv squared. Then with practice, you would need more energy than this to achieve this speed, because some energy will be transferred to the surroundings. Now you've got to say where that will go to. So it could be work done in heating the air, it could be energy transfer due to air resistance or drag. Now the next question says, on another occasion the falcon catches a small bird while gliding horizontally. Figure 4 shows the falcon and the small bird gliding horizontally in the same direction at constant speeds. The falcon collides with the small bird and grips it tightly. The mass of the small bird is 0.18 kilograms. The initial speed of the falcon is 25 meters per second. The initial speed of the small bird is 12 meters per second. So state the law of the conservation of momentum and then calculate the speed of the falcon immediately after this collision. So pause the video now, then unpause the video when you want to go through your answers. Right, so you've got to learn what the law of conservation of momentum is. Just a fact you've got to learn, and that is that the total momentum before and the total momentum after are constant as long as there's no external force applied on the system. Don't forget that second part. Now to calculate the speed, what you've got to do is look at what information you've got. So you've got the speed of the falcon, you've got the mass of the falcon, and you've got the mass of the small bird, and you've then got the initial speed, of the small bird. So what you can do is beforehand you can work out your total momentum by timesing the mass of the falcon by its speed and the mass of the small bird by its speed. You then add them together. Now if the momentum is conserved, the total momentum before is equal to the total momentum after, so that total momentum is then the same for the two objects combined afterwards. Then you would divide that by the total mass of the two objects to work out your speed, which is 23.2 meters per second. The next question says, Figure 5 shows an aircraft that is initially in level flight at constant velocity. Identify the forces P, Q, R and S acting on the aircraft. Then figure S is increased to a new constant value. State and explain any change in the horizontal and vertical motion of the aircraft due to the increase in S. So pause the video now, then unpause the video when you want to go through your answer. Right, so what forces will be acting on the object? Now again, it tells you that it's in the air, so acting down is going to be easy. R is going to be weight. S again is going to be the thrust of the engine or the motive force. Q is going to be the drag or the air resistance because we're in a fluid. Now again, because we're in the air and we're not on the ground, it can't be the reaction force. Because we're in air and not a liquid, it can't be upthrust, so therefore it has to be the force that acts on an object upwards when it is air, which is lift. So you can see it go through there. Now if S is increased, what will happen? Now again, think about it, it's 3 marks here. So firstly the speed will increase, or the aircraft will accelerate because there's now a resultant force towards the left. But because it's now accelerating, the air resistance or drag force Q will increase. Eventually they will equal out and you'll get terminal velocity. So they've got a new constant speed. But again, as there's a new speed, that faster speed, that tells us that lift is going to increase because the speed of the aircraft will affect the lift, so therefore it will also accelerate upwards as well. The next question says, on another occasion the aircraft is flying horizontally when force P is increased to 9.87 kilonewtons. The aircraft climbs with constant vertical acceleration and the weight of the aircraft is 9.60 kilonewtons. Show that the vertical acceleration of the aircraft is approximately 0.28 meters per second squared and that the aircraft climbs with a constant acceleration through a vertical distance of 500 meters. Show that the magnitude of the vertical component of the velocity of the aircraft at the end of the climb is approximately 17 meters per second. So pause the video now, then unpause the video when you want to go through your answer. So in this question, what can we do? Well, we're given the force, okay, and we're given the acceleration, and we need to work out. So we need to work out the acceleration, and we're given the mass. So what we do firstly is we've got the weight, so we can then convert that back into the mass by saying the weight is going to be equal to mass times by gravity. So therefore, mass is weight over gravity. Again, convert the kilonewtons into newtons by saying it's times 10 to the 3. So we get our mass to be 979 kilograms. We know what F is. Now we're going to remember F is the resultant force, so it's going to be the force upwards minus the force downwards, so therefore it's 9.87 minus 9.60. We then convert that into kilonewtons to see that it's 270 newtons. We then say F equals ma, work it through, and we get 0.276 meters per second squared. The next question, again, it says it climbs through a distance of 500 meters, show that the magnitude of the vertical component at the end of the climb is 70 meters per second. Now we can use SUVAT. We look at what we have. We've got S. Yeah, yes we do. We've got A, yes we do. We've got U, yes we do. We want to work out V. So what can we do? Well, V squared equals U squared plus 2AS. Pop in all the numbers and you get 16.7 meters per second. It's very important you write out the equation and you then pop the values into the equation. The next question says, during the climb, the aircraft has a constant horizontal component of velocity of 70 meters per second. Calculate the aircraft's resultant velocity at the end of the climb. So pause the video now and then unpause the video when you want to go through your answer. Right, so when you're doing this question, you can always think you've got your vertical component, you've got your horizontal component. Now there's two ways in which you can do it. You can either draw a scale diagram if they're not at 90 degrees to each other, but because they are at 90 degrees to each other, the easier way would be to use Pythagorean theorem. So you've got your constant horizontal component to be 70, you've got your vertical component, to be 16.6, so therefore to work it through, it's 70 squared plus 16.6 squared, all square rooted is 72. You can then, if you draw your right angle triangle, realize that the opposite is going to be the vertical, which is 16.6, and the adjacent is the horizontal, which is 70. So tan to the minus 1 is 16.6 over 70, because tan is equal to opposite over adjacent, TOA in SOHCAHTOA, so you get 13 degrees from the horizontal. We're now going to look at some questions involving electricity. So figure 5 shows the main parts of an X-ray tube. Electrons are emitted at the cathode and accelerated onto the anode. The operating voltage between the anode and cathode is 80 kilovolts. The tube current is 100 milliamps and the tube is switched on for an operating period of 5 milliseconds. Calculate the number of electrons that reach the anode during this operating period. Energy that is not emitted in the forms of photon is transferred to internal energy. The efficiency of the X-ray tube is 2%. Calculate the increase in the internal energy of the anode. Then the tube current is now increased. The operating voltage and the operating period are unchanged. State and explain any effect that the increased tube current has on the X-rays produced. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first one, what do we have? Well, we know that we have our current and we know we have our time. So we can therefore say that Q equals IT. Now again, to convert the milliamps into amps and the milliseconds into seconds, and we work it through to be 5 times 10 to the minus 4 coulombs. Now we know that one electron has a charge of 1.6 times 10 to the minus 19 coulombs. So therefore the number of electrons is going to be the total charge, 5 times 10 to the minus 4, divided by the charge of one electron, 1.6 times 10 to the minus 19, to get 3.1 times 10 to the 15 electrons. Now remember that in this case that we've got an efficiency of 2%. So 98% of the energy is going to the internal energy. So the first step is to work out your total energy. Now you can say energy is equal to QV. So we've got Q, we've got V. Remember we're going to convert our kilovolts into volts, and we've got our charge from the previous question to work out the energy to be 40 joules. Now 98% of that goes to the internal energy. So to convert the percentage into just a value, it's 0.98, because percent means divide by 100, so therefore it's 0.98 times by 40 is 39.2 joules. Now what will happen to the increased current on the X-rays produced? Well, if you have an increased current, well, there's more electrons emitted, so therefore more photons will be emitted, so therefore the intensity of the X-ray beam will increase and the frequency of the photon will be unchanged, because you're not changing how much energy the electrons have and therefore the photons have, rather you're changing how many of them hit the surface. The next question says, superconductors can be used in electromagnets in some types of trains. Explain what is meant by a superconductor and explain why superconductors are used in these electromagnets. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's a superconductor? You've got to learn this definition. It's a material whose resistivity is 0 below the critical temperature, and you've got to learn all those words. Now, why are superconductors used in these types of magnets? Well, it can generate strong magnetic fields, so they can stay in large currents because there's very little energy lost due to resistance, because there's no resistivity, so therefore there's no damage due to overheating due to energy transfer and energy dissipation. We're now going to look at some questions regarding further mechanics. So figure 1 shows a student moving a bucket of water in a vertical circle at a constant speed. The centre of the circle is marked with an X and the bucket is attached to a length of string. The water moves in a circle whose centre is at X. Draw on figure 1 an arrow to show the direction of the resultant force acting on the water. Then at the top of the circle, the angular speed is just sufficient to keep the water in the bucket. Explain why the centripetal force on the water is equal to its weight at the top of the circle. So pause the video now, then unpause the video when you want to go through your answer. Right, you can see straight away that it's going to be a centripetal force, and the resultant force of a centripetal force is always acting towards the centre of the circle, so it's acting towards X. Now, why is the centripetal force of the water equal to the weight at the top of the circle? Well, it's the idea that the reaction force is at that point 0, so therefore the only force that's acting on the object is the weight, and the weight therefore is the resultant, and the resultant force towards the centre is called the centripetal force, so it all works through. The next question says, the radius of the circle is 0.85 meters. Calculate the angular speed of the water. Then the student gradually increases the angular speed until the string breaks. The student plans to repeat the procedure. He wants to achieve a greater angular speed without breaking the string. He plans to use a new piece of the same type of string and the same bucket. Discuss 2 changes that the student can make to move the water in a vertical circle at a greater angular speed without the string breaking. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, we know that the weight is equal to the resultant force. So we know that the weight is equal to mass times acceleration. So therefore we can say that mg is equal to mr omega squared. Now the 2 m's will cancel through to say g is equal to r omega squared. So omega, which is what we're trying to work out the angular speed, is the square root of g over r. Pop in the values that we know, and then you get your answer to be 3.4 radians per second. Now for this next question, we know that the tension in the string is equal to 2 things. It's equal to the weight, which is mg, plus the centripetal force there, which is mr omega squared. Now when they are at maximum value there, maximum tension, which is important because you want to work out the maximum, because that's when the string is going to break at the maximum tension, not the minimum. The maximum is going to be when the 2 are added together, so mg plus mr omega squared. So what can we do? So we can reduce m, because if we reduce m, we'll reduce the tension, so it's less likely to break. Or what we can do is we can reduce the radius of the circle r, because again in mr omega squared, if we reduce r, we'll reduce the maximum value of t, so it's less likely to break. Obviously we can't actually do anything with omega, because it's already said we're going to have a greater angular speed, so we can't do anything with that. Alright, the next question says, figure 2 shows a tuning fork with a small piece of clay attached to it. The tuning fork is made to vibrate. The clay string stays attached to the tuning fork, and the figure 3 shows the tuning fork and the clay vibrating. Figure 4 shows the variation of acceleration of the clay with displacement from its equilibrium position. Explain how figure 4 shows that the motion of the object of the clay is consistent with the conditions for simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know here what the condition of simple harmonic motion. So because we know that simple harmonic motion shows acceleration and displacement are directly proportional to each other, but one is in the opposite direction to each other, well, to show direct proportionality, we should have a straight line through the origin, which we do. Now to show that one is in the opposite direction, it has to be a negative gradient, so you can see here that it's sloping downwards, so therefore it's proven the condition of simple harmonic motion. The next question says, show the frequency of the vibration of the clay is approximately 700 Hz, calculate it in meters per second the maximum speed of the clay, then label with P on figure 4 the position of a point in which the clay is travelling at its maximum speed. So pause the video now, then unpause the video when you want to go through the answer. Right, how to answer this question? Well, we know that we can work out our acceleration and displacement from the graph. So we can therefore say A is equal to minus omega squared x, and omega equals 2 pi f, because omega is just going to link into that with that particular equation. You can sub it in, so therefore acceleration is equal to minus 2 pi f squared x. We can then read off a value of a from the graph, read off a corresponding value of x from the graph, rearrange to make f the subject, and we get 660 Hz out as the answer. The next question says calculate the maximum speed. Now we know that the Vmax from the equation sheet is equal to A omega, or 2 pi f A. Now we know that the amplitude, which is A, is 1 millimeter from the graph because it's the maximum amplitude. Now we also know what F is from the previous question, so therefore we can work it through and we get 4.2 meters per second. Now label with P on figure 4 the position of the point where the clay is traveling its maximum speed. Well, the clay is going to be traveling the maximum speed at 0, 0. Why is that going to be? Because it's traveling at its maximum speed where the acceleration is going to be 0. So that occurs when there's no displacement. So it's going to be at the 0, 0 point, because remember, acceleration is directly proportional to the negative displacement. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-level physics examination style questions, assess our own understanding on A-level physics, and understand what topics we need to improve upon for AQA A-level physics. So thank you very much for watching this revision session on paper 1 for AQA A-level physics. Thank you very much and have a lovely day. Hello and welcome to this revision session for paper 1 in AQA A-level physics. So in today's revision session we're going to look at how to answer examination questions on A-level physics paper 1. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for AQA A-level physics. So how should you carry out this revision session? Well, when completing this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful, any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you revise AQA A-level physics? So the first step you should be doing is you should be looking at the knowledge, so learning the key facts. So use revision guides, class workbooks, student prep notes, the textbook to learn the key ideas of the course, such as making mind maps and writing out the notes yourself. Then you should be testing yourself, so use the Caboodle platform, use Seneca, use student knowledge checkers to quickly test your own knowledge, and you can do this from your own cue cards. The third step is then practicing, using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download past exam papers to do this. So you should be revising A-level physics by learning the key facts, testing yourself, and then practicing examination style questions. So let's now have a look at some questions for AQA A-level physics paper 1. So the first topic we're going to look at is particles and radiation. So an isolated metal plate is given a negative charge. Electromagnetic radiation is instant on the plate. The plate loses its charge due to the photoelectric effect. Discuss how the rate of loss of charge of the plate depends on the frequency and the intensity of instant radiation. In your answer, explain why the plate loses its charge, the photoelectric effect occurs only for frequencies greater than a particular value, and that the rate of loss of charge increases with the intensity of radiation above that particular value of frequency. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that what you've got to do in these types of questions is ensure you answer questions in a coherent order and structure, and also answer each bullet point in the question that's given to you as a separate paragraph. So what you should be saying is that for area A, you're going to lose its charge because emission of electrons from the surface when the electromagnetic radiation is instant on the plate. Okay, so therefore the number of surplus electrons remaining on the plate will decrease with time, so therefore the negative charge will go down because the electrons emitted will carry the negative charge away. In terms of the frequency, we know that from the second question, why is only occur for frequencies above a particular value? Well, the minimum energy required to liberate the electrons from the atoms from the metal surface is required, and that is the work function. So a photon must be supplied to produce this, to give the electron its energy in a one-to-one interaction. So the energy of a photon, so therefore the energy supplied to the electron electron to be liberated is equal to hf, and therefore the minimum frequency required is going to be our threshold frequency. You can see how it's important that we learn the key terms to do with the photoelectric effect. Then in terms of intensity is how many photons hit the surface every second. So this tells us that the intensity increases, more photons hit the surface every second at the same energy, so therefore we've got to increase the number of photons per second even if the frequency increases, so that gives us more electrons released from the plate every second, so the charge will go down more rapidly. The next question says, charged particles are emitted from the metal plate with a maximum kinetic energy of 1.1 eV when radiation of frequency 1.2 times 10 to 15 Hz is incident on the plate. Calculate in EV the work function of the plate. So pause the video now, then unpause the video when you want to go through your answers. Right, this question is testing you on how you can A, use the photoelectric effect equation, but also how you convert EV into joules and vice versa. So what you've got to do is say what's 1.1 EV in joules. Okay, so you do 1.1 times by 1.6 times 10 to the minus 19. What we can then do is work out what our work function is going to be by saying that the work function is equal to the energy of the photon minus that kinetic energy. Now the energy of the photon is equal to hf, so it's the Planck's constant times by 1.2 times 10 to 15. So therefore you work it through and then you get that energy in joules. But it wants the energy in EV. So what you've then got to do is you've then got to divide your answer by 1.6 times 10 to the minus 19. So what you should be getting is 3.9 EV, because you work it through and you work out what your work function is, and then you divide it. So you work it through and then you can divide it by 1.6 times 10 to the minus 19 to get 3.9 EV. The next question says, figure 4 shows apparatus used to demonstrate the wave-particle duality of electrons. So the heated filament emits slow-moving electrons. In region P, the electrons are accelerated to a high speed. At Q, the fast-moving electrons are instant on the graphite target. R is a point on one of the bright rings that are formed where the electrons strike the fluorescent screen. The electrons demonstrate wave-like and particle-like behavior as they travel from the filament to the screen. State and explain in which of P, Q, or R the electrons are demonstrating wave-like behavior. The apparatus is adjusted so the electrons are instant on the graphite target with a greater speed. Explain why the bright rings formed on the screen now have a smaller diameter. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important you understand what's particle behavior and what's wave behavior. So Q is going to be where it's acting as a wave because it's diffracting out, and diffraction is a wave, it's a wave property only. Okay, so it's very important you understand that idea. So the diffraction is because the electrons move between the layers in the graphite, therefore they then spread out between the layers in the graphite, so diffraction is taking place. Now, why will the bright fringes form here? Again, it's very important you know that when we're doing wave-particle duality that we use our equation for de Broglie. So therefore we know the de Broglie equation for wavelength is equal to h over mv. So therefore we've got a decreased wavelength, and therefore the momentum of the electrons will increase to work it through like so, because if lambda is going down, well then mv has to go up from our equation because h is a constant. So therefore less diffraction occurs because there's a shorter wavelength now relative to the layers in the graphite. Now remember again that diffraction occurs when the gap and the actual wavelength are approximately equal in size. So now one has changed dramatically, they won't be approximately equal, so you won't get as much diffraction, and there that gives you your answer. The next question says a sample of bromine gas contains a mixture of two isotopes. An experiment is done to find the percentage of each isotope in the sample. In the experiment, the gas is ionized by a beam of electrons. Explain how the beam of electrons causes a particle of the gas to have a charge of plus 1e. So how would you work that through? So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, an electron in the beam will collide with an electron in the gas. So what will happen at that point is when the electrons interact, there will be an energy transfer between them. So it's a bit like the being excited. So an electron in the beam will transfer some of its kinetic energy to the electron in the gas particle. So as a result, that will cause excitation. And then what will then happen is one electron will then leave that gas particle and work it through like so. The next question says bromine has a proton number of 35. The two isotopes in the sample have different nucleon numbers. Calculate the number of neutrons for the isotope that has a greater nucleon number. Then deduce the percentage of each isotope in the gas and justify your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you find the nucleon of the more massive isotope. So we know that, for example, that the proton number is 35. So we then do 162 divided by 2, which is 81. So therefore, what we can then do is we can then work out our values like so. Then we do 100, or we could do 162 minus 70. So 2 times by 35 is equal to 92. We can work it out and we get it to be 46. Now, what's the percentage of each isotope going to be? Well, the percentage is the same for both isotopes. So each isotope makes up 50% of the gas by number. So therefore, what you can therefore say at that point is that 158 is made up of 2 atoms, the lighter isotope, and 162 is made up of 2 atoms, the heavier isotope, and the percentages are both 25% in the same ratio. So you could also indicate that half of 160 is made from the lighter isotope and all of 158 is made from the lighter isotope, and that gives you 50%, and therefore half of 160 is made from the heavier isotope and all of 162 is made from the heavier isotope, which again is 50%, indicating that's 50 and 50%. We're now going to look at some questions regarding waves. So, two transparent prisms A and B of different refractive indices are placed in contact to produce a rectangular block. Figure 12 shows the path of a ray incident normally on A, refracting as it crosses the boundary between the prisms. Firstly, explain how the path of the ray shows the refractive index of A is greater than the refractive index of B. So pause the video now, then unpause the video when you want to go through your answer. Right, well, how do you answer this question? Well, if you look at the diagram, what you'll notice is the angle of refraction is greater than the angle of incidence. So if you look on here, if you look at your different angles, you can see that's going to be taking place, and you can actually use that from your similar triangles to work that through. Or you could just say fundamentally that light is bending away from the normal when it speeds up, indicating that the refractive index of A must be greater because it's travelling faster in B. The next question says, show that the angle of refraction of B is about 60 degrees and draw on figure 12 the path of the ray immediately after it reaches P and justify your answer with calculations. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you can see what the angle of incidence is, and remember the angle is always from the normal, okay, to the ray, so it's not going to be 43 but 90 minus 43, which is 47. We can then use Snell's law to then work out our angle of refraction because we've got the refractive indices of both the objects. You can work it through, so therefore you can say 61.4. Then for the next question we can say that the critical angle is equal to 1 over n. We've got n again, so we can work out the critical angle to be 48. We therefore know our angle of incidence is going to be 76 degrees, so therefore it indicates that the ray is going to be reflecting off P to land on the top of where n is on the not to scale label when it meets the glass surface, because you can tell it won't be totally internally reflecting. Let's now have a look at some questions to do with mechanics and materials. So figure 8 shows a cyclist going up a hill. The angle theta of the slope of the hill is constant. The total mass m of the cyclist and the bicycle is 65 kilograms. Write an expression for the component of the total weight parallel to the slope. Then the useful power output of the cyclist is 310 watts. The cyclist has a steady speed of 1.63 meters per second. Assume that the air resistance is negligible at this speed and calculate theta. So pause the video now, then unpause the video when you want to go through your answers. Right, so this question is asking you pretty much to work out the components of the weight. So what you would do is you would say that, well, weight is going to be acting down, so vertically down like so. So what you can therefore do is make your right angle triangle, and you'll see straight away that it's going to be give you that you've got your opposite and you've got your hypotenuse, so you can say it's going to be sine, because SOHCAHTOA, sine is opposite over hypotenuse, so therefore you know what the value is going to be for the weight, because if you look down, work down 65 kilograms, so the weight therefore, or the force, is going to be 65 times by 9.8, which is going to be 640, so therefore we can say that weight is equal to 640 sine theta. Now in the next part, what we can do to work out theta is we know that power is equal to force times by velocity. Why do we know to use that one? Well, we know from the question we are given the power output and we've got the velocity, so therefore we can work out quite quickly. We're going to need to work out the force here, so therefore you work out what your force is at that point. So P equals FV to work out the force. Therefore what you can do is you can work out through your value like so by doing, for example, you can work it out by doing 65g sine theta is working out to F. You can work it through like that and you get your answer to be 17.4 degrees. Now the next question says, figure 9 shows an alternative zigzag path taken by the cyclist up the same hill. She maintains a steady speed of 1.63 meters per second. Discuss how her useful power output when taking the path in figure 9 compares with her useful power output in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so the important thing to note here is when you're taking the zigzag path, it's going to be a less powerful output, because what you can think about power is the work done per time. Now you're going to have the same work done, the same gain in your gravitational potential energy, because you're going to be doing the same ultimate change in height over in that particular time, but the time is going to take longer because you're going in a zigzag path, because your displacement is staying constant but your distance traveled has increased. So what's happening is you're gaining less energy every second, so therefore your power has gone down. The next question says, the cyclist reaches the top of the hill. She travels back down the hill in a straight line. The bicycle rolls free without the cyclist pushing the pedals or applying the brakes. Figure 10 shows the variation of her velocity with time as she goes down the hill. So determine the acceleration of the cyclist 10 seconds after she begins to go down the hill. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you're trying to work out acceleration and you've got a velocity time graph. So with the velocity time graph, you know the gradient is going to equal the acceleration, but it's a curving line. So how do you work out the gradient of a curving line? Well, you draw the tangent, okay, to the point which you want to work out the gradient for, which in this case is 10 seconds. You then work out your gradient of the tangent, okay, and then work it through and you get 0.21 meters per second. Now again, it's very second squared. It's then very important that you draw on your tangent carefully and you draw very clearly in your answer your gradient triangle. The next question says, energy transfers occur as the cyclist travels down the hill. Outline how these energy transfers explain the shape of the hill in figure 10. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to think about is as it goes down the hill, air resistance is going to increase with speed. So you can say for the resistive forces, drag is going to increase with speed. So energy is transferred from the cyclist to the internal energy of the surroundings by these resistive forces. Now you would say that initially you've got gravitational potential energy stored for your cyclist because it's high up, okay, but then that's going to transfer to the kinetic energy because it's then increasing speed as it moves down the hill. Now as the speed increases, less the gravitational potential energy will be transferred to kinetic energy as there's more resistive forces. So we can say that more will transfer to the internal energy of the air, and then at top speed the gravitational potential energy is transferred to the air or it's work done due to resistive forces because we're not going to be increasing speed anymore, so no further energy is going to our kinetic energy store. The next question says, figure 5 shows the worker of weight 750 newtons on a uniform platform. The weight of the worker is acting at a horizontal distance d from end A. Throughout the question, assume the platform is horizontal and that all cables obey Hooke's law. The platform weighs 1,800 newtons and is suspended by vertical cables P and Q. Each cable has an unstretched length of 3 meters. The horizontal distance between P and Q is 3.6 meters. The worker moves to a position where the tension in the left-hand cable P is 1,150 newtons. Calculate D for this position. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to look very carefully and go, we've got a weight, we've got a distance, and it's balanced. So we're going to be using the principle of moments. So what you can do is you can then look at what's the clockwise moments acting on the object, what's the clockwise moments acting on the object, and then equal the two with each other. So what you can do is you can see that, look at the clockwise, okay, and look at the anti-clockwise moments, and you can work it out as such. So if you took your moments, for example, about B, you could say it's 1,150 times times by 3.6. Why is that? Because you can see straight away that you've got your weight acting down there, okay, and it moves position when the tension is 1150. Okay, so you do 1150 times by 3.6, okay, equals 1800, which is going to be, if you notice, the platform weight, then times by 1.8, because remember we assume the weight's acting from the dead center. So if we're taking it from B or Q, therefore the distance from the center to one of the edges is 1.8. Then you'll plus 750 times by 3.6 minus D, because we're now doing the weight of the worker times by the distance it is from one of the sides. You can work it through there, so you can say 1150 times by 3.6 equals 1800 times by 1.8 plus 750 times by X. You can then work it all through, work out what X is, and it's going to be 2.4 meters. Right, the next question says, figure 6 shows how the extension of P varies with D as the worker walks slowly along the platform from A to B. The worker moves to a position X where the strain in P is 6 times 10 to the minus 5. Determine D for position X. Then the cable material has a Young modulus of 1.9 times 10 to the 11 newtons per meter squared. Calculate the tensile stress in P when the worker is at X. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, you can see straight away that the extension is going to be 0.18 millimeters. How do you know that? Well, if you look through, you know what the value of D is going to be, okay, at position X, so you can work it out there, and then you can say, well, E is going to equal delta L over L, so therefore you can work it out, and then D is going to equal 1.8 meters. Then for the next question, we can say that the stress is going to be equal to 1.1 times 10 to the 7 newtons per meter. Again, because why is that? Well, we've got our strain, okay, from the previous question, 6 times 10 to the minus 5 there. We know that Young modulus is stress over strain, so therefore stress is going to be Young modulus times by strain. So you do 1.9 times 10 to the 11 times by 6 times 10 to the minus 5, and therefore you get your answer to be 1.1 times 10 to the 7 newtons per meter squared. The next question says, figure 3 shows a garden gate with a pulley system designed to close the gate. The pulley system raises weight A when the gate is open, and when the gate is released, A falls. The horizontal cable C passes over the pulley. The tension in the cable C causes the gate to close. Weight A is a solid cylinder with the following properties. Diameter is 4.8 times 10 to the minus 2 meters, length is 0.23 meters, and weight is 35 newtons. Table 2 gives the density of the 3 available materials. To use one of the 3 materials, which one of the 3 materials is used for A? So pause the video now, then unpause the video when you want to go through your answers. Right, so how to answer this question? Well, what you need to do firstly is you need to work out what the volume is going to be. So the volume is going to be equal to the area times by the length. So what we can do is we can then work out what our volume of A is going to be, because we can work it through by doing area times by length, and we get 4.16 times 10 to the minus 4 meters cubed. Okay, and that allows us to then work out what our mass is going to be as well, because we can say that, well, the mass is going to be the weight, which we got before, which is 35, divided by gravity, which is 3.6 kilograms. We can therefore say density is going to be equal to mass over the volume. So therefore we've got our mass, we've got our volume, we divide one by the other, and therefore we can work out which one's going to be the closest to, and we get our answer to be 8.3 times 10 to the 3, okay, which we can then work out to be brass, because it's very close to 8.6. The other way you could have possibly done it is you could have worked out your volume, worked out your mass, okay, for if it was particularly brass, for example, or iron or concrete, and then work it out what the mass should be, and then see which is going to be the correct answer. The next question says, figure 4 shows the pulley arrangement when the gate is closed. Pulleys P and M are frictionless, so that the tension in the rope attached to A is equal to the weight of A. A weighs 35 newtons and the weight of the movable pulley M is negligible. Calculate the tension in the horizontal cable when the gate is closed. Pulley M is pulled to the left as the gate is opened. Explain why this increases the tension in horizontal cable C. So pause the video now. When you want to go through the answer, unpause the video. So how do you answer this particular question? So the first thing you've got to do is think about how you would calculate the tension in the horizontal cable C. So to do this, you've got to consider the tension. Now again, what you've got to realise is that the tension is going to be linking into the angle. So we would do 35 cos 55 because of the angle it's at, because it's in the horizontal. Now because there's two ropes there, you don't have to double that answer. So you have to do 35 cos 55, then multiply it by 2. Now it says pulley M is pulled to the left as the gate is open. So how does this increase the tension? Well, once again, what you're going to think about is the angle, because it's asking about the component. So what would happen is the angle would decrease. So therefore, there's going to be a greater value of the force or the tension in the horizontal. So therefore, the tension in the cable must increase because there's more acting in the horizontal. Now the next question says, figure 5 shows a plain view with the gate open. The horizontal cable C passes over pulley R and is attached to the door at D. The angle between the door and the horizontal cable C is 12 degrees. The horizontal distance between the hinge and D is 0.95 meters. The tension in the horizontal cable C is now 41 newtons. Calculate the moment of the tension about the hinge. So pause the video now, then unpause the video when you want to go through your answer. Right, so how are we going to work this out? So what you've got to realise once again is that it's at an angle, so you've got to consider the component. So what you're going to have to be doing is you're going to have to work out the component of the force at right angles to the door. Now the angle you're given is not actually the one at right angles in that sense, so it'll be 41 cos 78, or you could do it as 41 sine 12, depending on how you want to work out your right angled triangle. So that gives our actual force not to be 41 as you might think in the question where it says that the tension is now 41 newtons, but rather the force that you would require is 8.5 newtons. Now moments are force times by perpendicular distance from the pivot, so it's 8.5 times by 0.95 meters, so your answer is 8.1 newton meters. Now the next question says, the same system is attached to an identical gate with stiffer hinges. Now the system does not supply a sufficiently large moment to close the gate. Discuss 2 independent changes to the design to increase the moment about the hinges due to the horizontal cable C. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important that when it says discuss, that means you've got to state what the change will be and explain why that will be the case. So you've got a couple of possible answers here. The first one will be to increase the weight or increase the tension. Now that would, because if you increase the weight, it increases the tension, therefore increases the moment. You could position the pulley a bit further out from the hinges, so therefore it would increase the angle, and therefore you'd have a greater component in the actual direction of the moment, so increases the moment. You could decrease the angle again by putting P and a fixed point closer together, so therefore would increase the tension, increase that force to increase the moment. Or you could move D further from the hinge and make C longer. Again, that would increase your perpendicular distance, so it would increase your moment. You've always got to think to yourself, the moment is the force times by the perpendicular distance. So if you wanted to increase your moment, you've either got to increase your force or you've got to increase your perpendicular distance between the line of action and the pivot. So you've got to think about how you could do that. We're now going to look at questions concerning electricity. So figure 11 shows a variable resistor has a maximum resistance 25 ohms. A sliding contact P is mounted on a thick copper bar. P can be set to any position between X and Y. Figure 12 shows a variable resistor being used to investigate the variation of current with voltage for a filament lamp. The normal operating voltage of the lamp is 12 volts. The 12 volt battery has a negligible internal resistance. The position of P is adjusted so that the reading on the voltmeter is at its minimum value at 0.75 volts. Calculate the resistance of the lamp when the voltmeter reading is 0.75 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, it's fundamentally a potential divider circuit. You've got to realise that because you can see there you've got your potentiometer in the circuit. So what you could do is you could use V equals R1 over R1 plus R2 times by V in. So what you could then do is work out that value because you know what the resistance is of each one. You know the total resistance, you know the starting volts. So you see on here, you can see it's 12 volts there. So you can work it all through and you get your answer out, okay, to give you okay, your value for V, then you can work out what the value of the resistance is going to be. So you would get out ultimately 1.7 ohms, which is what the calculating value would like to work out. Or you could just do it as a ratio, because what you would know is that for a circuit, the potential difference is directly proportional to the resistance. So you could just ratio the values and work out your value as such like that. The next question says, figure 13 shows the variation of current with voltage for the lamp between 2 volts and 12 volts. Calculate the resistance of the lamp when the voltage across the lamp is 8 volts. Then explain in terms of electron movement why the resistance of the filament lamp changes as the voltage changes shown in figure 13. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out the first one? Well, you know you've got current and you've got potential difference. So what you can do is you can read the values off the graph. So what you can see straight away is at 8 volts, what is the current going to be? Well, it's going to be 1.7 amps. So at that point, we can say V equals IR. So R equals V over I. So at that point, you can work it through and you get your answer to be 4.7 ohms. Now, in theory, because it's a curving graph, you could also do a gradient of a tangent which hits the point at the at 8 volts. However, you've got to be careful. It's the 1 over the gradient. You have to 1 over your answer if you did it by that methodology. The next question is asking to explain why the resistance changes. Now, it's important to note that as the potential difference increases, the current does not increase at the same rate. So therefore, the resistance is going up. So as the voltage increases, the current increases and therefore increases more electrons through the wire. This then leads into what resistance fundamentally is, the collision between the charge carriers and the lattice ions. So there'll be more collisions between the electrons and the lattice ions because the vibration of the lattice ions is at a greater amplitude. So the important thing to note is that the number of collisions every second between the lattice ions and the charge carriers increases. Now remember, it's always per second. It's the frequency of collisions that increases, which causes your resistance to increase. The next question says figure 14 shows an alternative circuit used to investigate the variation of current with the voltage for the lamp. The circuit components are the same as in figure 12 when the voltage across the lamp is 12 volts and its resistance is 6 ohms. P is moved to position Y, calculate the total resistance of the circuit, then calculate the power transferred by the battery when P is at position Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you're going to do in this case is that if P is moved to position Y, straight away what we've got is we can work out our total resistance, and it's in a parallel circuit now. So it's 1 over R total equals 1 over R1 plus 1 over R2. At that point you can work out what your different values are, because we know that one resistor has resistance of 6 ohms and the other one is 25. So therefore it's 1 over 6 plus 1 over 25. Add them together, flip it over to make it R. So you get 4.8 ohms out, which makes sense because it's in a parallel circuit and it's lower than any individual. Now, what's the power transferred at this point? Well, we know that we've got R and we've got V. We know R we've just worked out to be 4.8 ohms. We know V from the question is 12 volts because that is the volts supplied by the battery. So we can do the equation from the equation sheet. P equals V squared over R. Pop in the values, work it out, and you get 30 watts. The next question says, a student wants to control the brightness of the lamp. He gives 2 reasons why the circuit in figure 14 is better than the circuit in figure 12 for controlling the brightness. The 2 reasons are that the figure 14 circuit can achieve a greater range of voltages across the lamp, and that the figure 14 circuit is more efficient at transferring energy to the lamp. Discuss without calculation whether either of these 2 reasons is correct. So pause the video now, then unpause the video when you want to go through your answers. So how would you work this through? So the idea is that there's a wider range, okay, in figure 14 circuit. Why is that? Because the voltage range in figure 14 circuit is 0 to 12 because we're using our potentiometer, whilst in figure 12 circuit it's 0.75 volts to 12 volts, and you can't get a value between 0 and 0.75. So when you're using it as a potentiometer, the important advantage is you can always get every value from 0 to the EMF of the power source. However, okay, the idea is that figure 14's has a lower efficiency than figure 12's. That's an important idea because At any particular voltage across the lamp, more power will be dissipated in figure 14 as any voltage across the lamp is always 12 volts across that resistor, so therefore it'll produce more heating, so therefore there'll be less energy going to the useful part of the circuit, so therefore it won't be as efficient. The next question says, a student assembles the circuit in figure 6. The battery has an internal resistance of 2.5 ohms. Show that the resistance of the 6.2 volt 4.5 watt lamp at its working potential difference is about 9 ohms, and that the terminal PD across the battery is 6.2 volts, and calculate the EMF of the battery. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've been given the potential difference, you've been given the power, and you need to show that the value of R. So we can again say P equals V squared over R, rearrange that to make R the subject, and R equals V squared over P, pop the numbers in, and we get 8.5 ohms. Now, how do you work out the EMF of the battery? So what you can do is you've got now your potential difference, and you've got your resistance, so you can calculate the current in the lamp, or the current in the 12 ohm resistor, or you can calculate the total resistance and then work out the total current, and therefore what we can then say is that EMF is equal to terminal PD plus loss volts, which is IR. So at that point, once you've worked out your current, okay, you can work it out by working it through by saying, well, what's the terminal PD? Well, you can work out what the terminal PD is because you can work out what the EMF, you can work out what the value is outside the circuit because you've got the working values there. So therefore you can work out your terminal PD to be 6.2 volts. You know what your current is because you can work it through to be 1.24 amps by working out the total current, okay, through the circuit, then adding them together. So you work the current in the lamp and the current in the resistor and add them together. Then you can times that by the internal resistance there, and then you get your answer out to be 9.3 volts. The next question says the student makes a variable resistor to control the brightness of the lamp. Figure 7 shows her circuit. She uses a resistance wire with a diameter of 0.19 millimeters to make the variable resistor. A 5 meter length of this wire has a resistance of 9 ohms. Calculate the resistivity of the wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we've got here is we've got a diameter, we need to work out, we've got a length and a resistance, we need to work out the resistivity. So the first thing we need to do is work out our area, because if you look on the equation sheet, resistivity is equal to RA over L. So area is pi r squared because it's we assume it's going to be a circular cross-sectional area for a wire, so therefore we work out our resistance is half the diameter, we put it into meters, so 0.19 divided by 2 times by 10 to the minus 3, and we work it out to be 2.84 times 10 to the minus 8, pop the values into the equation, and we get 5.1 times 10 to the minus 8 ohm meters. The next question says, figure 8 shows a 5 meter length of wire wrapped around a tube to make the variable resistor. Two plugs connect the variable resistor into the circuit. A movable copper contact is used to vary the length of wire in series with the lamp. When the contact is placed on the tube in one particular position, the lamp is dim. The contact is then moved slowly as shown in figure 8 to the right. Explain without calculation what happens to the brightness of the lamp as the contact is moved. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to understand is that if we move it to the right, the resistance is going to increase because you've got a greater length, so there's therefore more collisions between the charge carriers and the lattice ions. So if the resistance goes up, the current will therefore go down, so the brightness of the bulb will decrease. Or you could argue that there's a greater PD across the plugs because we'll consider this as a potential divider, so the wasted potential difference is larger, so therefore the useful potential difference is lower, so therefore the lamp will be dimmer. The next question says, the student makes a different circuit by connecting the variable resistor in parallel with the lamp. The contact is returned to its original position on the tube as shown in figure 8 and the lamp is now dim. The contact is again slowly moved to the right. Explain without calculation what happens to the brightness of the lamp as the contact is moved. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to consider it's now in parallel. So what happens is the resistance will increase as you move it to the right, which reduces the current in the circuit and the battery. Or you could say it increases that external circuit resistance, so it reduces the potential difference dropped across the internal resistance of the cell. So therefore you've got a greater potential terminal PD because there's less energy being dissipated in the power source, so the lamp will be brighter. Let's now have a look at a few questions on further mechanics. So a teacher sets up a demonstration to show the relationship between circular motion and simple harmonic motion. She places a block on a turntable at a point 0.25 meters from its center as shown. The turntable rotates with an angular speed of 1.8 radians per second and the block does not slip. Calculate the time taken for the turntable to complete one revolution. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to consider how you work out angular speed. Angular speed is the change in angle divided by the change in time. So we can rearrange this and we can say that time is equal to the change in angle over the change in speed. So therefore we know what our change in angle is in one complete revolution. It is 2 pi radians. So therefore do 2 pi radians over 1.8 radians per second to get 3.5 seconds. The next question says, Figure 10 shows a plane view of the turntable and the block. The turntable rotates in a clockwise direction. Draw an arrow on Figure 10 to show the direction of the resultant force on the block. The mass of the block is 0.12 kilograms. Calculate the magnitude of the resultant force on the block. Pause the video now, then unpause the video when you want to go through your answer. Right, it's always very important you're aware of the direction of the resultant force on an object moved with circular motion. Well, the centripetal force or the resultant force causing a circular motion always acts towards the center of the rotation, so your arrow should be pointed to the center of the turntable. Now we need to work out this resultant force, and there's a couple of equations we can use. We could use F equals mv squared over r, because that is just for a centripetal force, or we could use m omega squared r. Now if you think about it, we got m, so we could use either of them, but we've just been given in the previous question omega. We've got total 1.8 radians per second, and we got the radius as well, so we can use that to work out our answer to be 0.097 newtons. Now the next question says, describe with reference to one of Newton's laws of motion the evidence that a resultant force is acting on the block. Then the teacher adjusts the angular speed of the turntable so that the block completes one rotation every 2.50 seconds. She sets up a simple pendulum above the center of the turntable so that it swings in phase with the movement of the block. Calculate the length of the simple pendulum. So pause the video now, then unpause the video when you want to go through your answer. So how do you answer this particular question? So you've got to understand what's causing a resultant force. Well, it's the idea that is if it's moving in a circle, well then the block is constantly changing direction. And the only thing that can cause an object to change direction or accelerate is a resultant force, which is Newton's first law of motion. And it's important to actually state what that law of motion is and link it into it. So at that point we must have, due to Newton's first law of motion, a resultant force acting on the object. Now to work out the length of this simple pendulum, what you've got to do is use your equation t equals 2 pi times by the square root of L over G. At that point we rearrange it and make L the subject. We've got t, we know 2 pi, and we know G to be 9.81. So therefore we pop in our values and we get 1.55 meters. So it's very important you refer to your pendulum equation, which is given on the equation sheet. The next question says, a lamp is used to project shadow images of the block and pendulum bob on a screen. Both shadows appear to move with simple harmonic motion across the screen. Figure 11 shows the images on the screen in one instance. Initially the shadows move in phase with the same amplitude. Air resistance affects the motion of the pendulum, suggests the effect this has on the amplitude relationship and the phase relationship between the moving shadows. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about what's taking place. So if you have air resistance acting on the pendulum, well, the pendulum shadow amplitude becomes less because it's not going to move as much because energy has been dissipated out of the oscillator into the surroundings via this air resistance. And also the time period would decrease and the frequency would increase, so that would therefore give our phase to change. Now, it would It would, if you were to think about it, if the time periods and frequencies remained identical, the shadows would remain in phase. Now, if you think about it, the time period is going to again decrease because the energy has been removed from the system. It is being damped in that instance. So, if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you very much for watching this revision session on A-level physics for AQA, and it is on paper 1. So thank you very much for attending this revision session and have a lovely day. Hello and welcome to today's revision session on the paper 1 topics for AQA A-level physics for the 2022 examinations. So in today's revision session we're going to look at how to answer examination questions for paper 1 of AQA A-level physics. So if we've been successful and we've learned in today's lesson, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So how do you carry out this particular revision session? Well, when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side, and in the left hand side section write down your answers and your working out to questions in this revision session. When you do this, make sure you write your answers in full sentences and show your full working out, and whilst in the right hand side write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-level physics? So first step is learn the key facts. So use your revision guides, your class workbooks, your student prep notes, your textbooks to learn the key ideas of the course. This could include making mind maps or writing out notes yourself. Step 2 is to test yourself. So use your Kaboodle e-learning platform, Seneca platform, a student knowledge checker to quickly test your own knowledge. And you may do this when making your own cue cards. And step 3 is practice examination style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. So you may wish to download your own exam past papers to do this. So this idea of learning the key facts, then testing yourself and retrieving your knowledge before practicing exam style questions and reflecting on your performance is the way to revise AQA A-level physics. So let's have a look at a few questions on the different topics which will come up on the exam in the summer of 2022. So let's first look at particle physics. So the first question says photoelectrons are emitted from a sodium surface when it is illuminated with monochromatic electromagnetic radiation. The stopping potential of these photoelectrons is 3.42 volts. Show that the maximum kinetic energy of the photoelectrons is approximately 5.5 times 10 to the minus 19 joules, and then calculate the wavelength of the radiation that's incident on the sodium surface when the wave function of sodium is 2.36 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, in this particular question, you've got to be aware that you're trying to show that the maximum kinetic energy of the photoelectrons is that particular value. Now, how you can work it through is as follows. Well, you are told that the stopping potential is 3.42 volts. Now, you can equate the stopping potential to the kinetic energy when you say that the electrical potential energy equals the kinetic energy. Okay, so you would convert the stopping potential into electrical potential energy, which is equal to the kinetic energy, by multiplying the stopping potential by E, the charge of the electron. So to get your answer, you would do 3.42 times by 1.6 times 10 to the minus 19, which is the charge of an electron, and that gives you 5.47 times 10 to the minus 19 joules. Now in this next question, you've got to be aware of the equation for the photoelectric effect, and that is that the energy of the photon hf is equal to the work function plus the kinetic energy. Now in the previous question you've worked out your kinetic energy. Now it's important to note that you've got to convert your work function into joules by doing 2.36 times by 1.6 times 10 to the minus 19 to convert it back into joules. We can then work out what our value for hf is. We can then say E is equal to hc over lambda. So E, which we work through there, or we could can also, which E equals HF, we can then use that to then work out lambda by using that particular equation. Another way you could have possibly done it is to work out the frequency, because you're going to have the value of E in total, because you'll add your stopping potential in joules to your your work function in joules to your kinetic energy in joules. You would then add that to find the total energy. You could then divide that by Planck's constant H to work out F, and then do C equals F lambda, okay, and say lambda equals C, 3 times 10 to the 8, okay, over the frequency you've calculated to get 2.15 times 10 to the minus 7 meters. The next question says, the frequency F of the electromagnetic radiation is now varied. The maximum kinetic energy of the photoelectrons is measured for each value of F. Figure 2 shows the variation of the kinetic energy with F. Magnesium and cesium surfaces are also illuminated with the electromagnetic radiation, and photoelectrons are emitted from the surface. Draw on figure 2 lines to show the variation of EK max with F for magnesium and for cesium, and label your lines, and you're given the work function of magnesium and cesium. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you note, okay, on a kinetic energy against frequency graph for the photoelectric effect, you know what each part of the graph represents. So you should be aware that the negative y-intercept is your work function. You should know that your x-intercept is the stopping, it's going to be the threshold frequency, and then the gradient of the line is going to be Planck's constant. Now, because Planck's constant is a constant, as the name suggests, that indicates to us that the gradient of the three lines, the one on the graph and the one for magnesium and cesium, are going to be the same gradient. So that's important. The next thing is that the work function is the negative y-intercept. So your magnesium should be intercepting your y-axis at minus 3.68, and your work function of cesium will be intercepting minus 2.4. Obviously, in theory, it should be in joules on the y-axis, but because we're just draw and sketching them in, you don't need to convert them. But the important thing to note is the gradient for both the lines is the same, because the gradient is the Planck constant, whilst the magnesium line is lower because it's got a higher work function. The next question says, figure 3 shows apparatus that can be used to investigate the photoelectric effect. The experiment is conducted in a vacuum. The photoelectrons that are produced move towards the conducting cage. The stopping potential V of the photoelectrons is measured using a circuit connected to the metal and the conducting cage. A small amount of air now leaks into the apparatus. Explain how the measured value of V is affected by the presence of air. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important to understand what is actually going on. The measured value of V, which is the stopping potential, is when all of the kinetic energy of your photoelectrons, when they're being emitted from the metal surface, has that converted into electrical potential energy due to repulsion. So as a result, we've got to understand what happens if air goes into the apparatus. Well, the air particles will go into the apparatus, they will collide with the photoelectrons moving through the apparatus, and as they collide, it will dissipate some of the kinetic energy out of the photoelectrons because they're colliding with them. So that means there's going to be less kinetic energy for the photoelectrons to transfer into electrical potential energy. So therefore the stopping potential is going to be lower because there's not as much kinetic energy there to transfer into electrical potential. The next question says, figure 1 shows some of the energy levels of a single atom. The atom is in its ground state. A photon of 8.81 eV is incident on the atom. Describe a likely outcome of this event. And then multiple atoms with the same energy levels are shown in figure 1, and they return to the ground state. How many different photons can be observed? So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you understand what could happen. So you've got to look at either the idea of excitation taking place or ionization taking place. Now, for excitation to take place, it's got to be the exact energy level difference for this to take place, whilst for ionization, it's going to be that value or more. Now, that is for a photon. Obviously, if an electron collides with it, it's a different situation entirely, but we're just talking about a photon being absorbed by the atom. So you've got to look here, and you've got to look, is there a gap of 8.81? Okay, and you would say yes there is, because from minus 10.38 to minus 1.57, the difference, the gap is 8.81. So you would say that the photon is absorbed and the electron is excited from its ground state into the fourth energy level, the minus 1.57. Now again, please remember it's going to be the exact energy level difference if you're absorbing a photon from this. Now the next question, how many different photon wavelengths can be observed? Well, what we've got to say is we've got, if the photon is emitted, okay, when it is being de-excited, so you've got to look at how many possible events could be de-excited. So we'll go from the highest level, which is at 0.00, okay, and you can see how many there's going to be as it de-excites back down to the ground state, and you can see how many there are going to be, and there's going to be 6. The next set of questions will be on force, energy and momentum. So the first question says, figure 6 shows two identical dummies, A and B, in a moving car. Dummy A has a seatbelt, dummy B does not have a seatbelt. Figure 7 shows how the horizontal force on each dummy varies with time as the moving car is brought to rest. So the area under curve A is equal to the area under curve B. Explain why. Then secondly, explain why the same work is done on both dummies even though the maximum force on dummy A is less than the maximum force on dummy B, as shown in the graph of figure 7. So pause the video now, then unpause the video when you want to go through your answer. Right, so the important thing to note is for a force time graph, what can we find out from the graph? So the idea is the area under the graph for a force time graph is the change in momentum or the impulse. Now, because this is a collision, the change in momentum is the same. Now, why do we know that? Well, we know that because when the car crashes, the momentum has gone to 0. And we know that the initial velocity, okay, for both dummies is going to be the same because they're in the same car, and the masses of the dummies are the same as well. So they'll have the same momentum at the start, the same momentum at the end, so they'll have the same change in momentum. That was indicated when it said they are identical dummies. Now the next question is, why was the same work done on both the dummies? Well, it's because they've lost the same amount of kinetic energy. So you could say that the work done on the dummies is force times by distance or force times by displacement. Now you could indicate that whilst force A has a small force acting on it, as shown in figure 7, it will move a large distance compared with B, which has a large force and a small distance. So you can see in that situation that because work done is force times by distance, okay, that the two values will equate each other out. Now you'll note, okay, that it has to be the same loss in kinetic energy because they'd start with the same kinetic energy at the beginning and have the same kinetic energy at the end. Why the same at the start? Well, they've got the same mass and the same velocity. And why the same at the end? Well, they're both 0 because they've stopped moving. The next question says, from this particular example, state Newton's first law of motion, and then secondly, explain how Newton's first law of motion applies to dummy B, which does not have a seatbelt on. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is Newton's first law of motion? This is something you've just got to memorize, and that is a body will remain in a state of rest or with uniform motion or with a constant velocity unless it's acted upon by a resultant force. An object will have inertia unless it's acted upon by a resultant force. So how does this link to dummy B? Well, dummy B will carry on moving because it has no seatbelt to provide a resultant force on it to change its velocity. So as a result, okay, you would say that B is going to have inertia because there's no resultant force acting upon it until it experiences a force, which will be when it hits the windscreen. The next question shows the following. Figure 2 shows a ball thrown with a velocity of 15 meters per second at an angle of 20 degrees to the horizontal. It reaches a wall 0.15 seconds after being thrown. Throughout this question, assume the air resistance is negligible. So calculate the horizontal distance d travelled by the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? So we're doing the horizontal distance. Now we'll notice in this particular situation that we would note that that there's going to be no horizontal force acting on this object. The only forces are in the vertical because it's a projectile. So because the horizontal force is going to be overall 0, we can use the equation that speed is equal to distance over time because there's no acceleration. So we can therefore say distance is equal to speed times by time. Now we know what the time is, 0.15, but what is going to be the speed? Now it's not 15 meters per second because that's at an angle. So what you've got to do is you've got to work out the horizontal component of that 15 meters per second. So you would do 15 cos 20, and that is your horizontal component using trigonometry, times by 0.15 to get 2.1 meters. The next question with the same example says calculate the height gained by the ball and then calculate the speed at which the ball hits the wall. So pause the video now, then unpause the video when you want to go through your answer. Right, so how should you answer this particular question? Well, in the first section, what we need to do is we're trying to work out the height. So we're trying to work out the height, we've got a time and we've got a starting velocity. So we should be using SUVAT. So you do S, U, V, A and T. And what you know is you know your value for U, because we know it will be 15 sine 20 because we're working now in the vertical, because we're going to work the vertical height out. We know what our value for A is going to be. It's going to be minus 9.81 because it's acting against the acceleration due to gravity, because the force acting on it is the weight of the object. And we also have the time, which is 0.15 seconds. So therefore we want to work out height. So what SUVAT equation can we use? Well, we can do S equals UT plus a half AT squared. We work out what our vertical velocity is by doing, like we said before, 15 sine 20, and then we pop all our values in and we get 0.66 meters. Now again, the next question, calculate the speed at which the ball hits the wall. We can now use SUVAT again. Instead of trying to work out S in the previous question, we can now work out V. So what we can do is we can do V equals U plus AT. So we can do V equals U plus AT. We know what U is. It's 5.13 from the previous question, plus AT. Now what's A? It's minus 9.81. Why minus? Because it's going against gravity, times by 0.15 T. So that will give us our value to be 3.65. Now that actually isn't the overall velocity that it hits the wall at. That is actually the vertical velocity. So what we need to do is we now need to do Pythagoras, because we actually need to work out what the overall velocity is going to be, because we know what our value for the vertical velocity is. It's 3.65. We know what our horizontal velocity is going to be, 14.1 from the previous question that we've done. So to work out the overall velocity of them both combined, we do Pythagoras, because we would say a squared equals b squared plus c squared. So we can say that it's going to equal the square root of 3.65 squared plus 14.1 squared, and we get 15 or 14.6 meters per second. We're now going to look at some questions on the topic of current electricity. So the first question says a heating element in an electrical heater consists of a coil of wire. The heating element transfers a power of 1 kilowatt when directly connected to the main supply of 230 volts. Show that the resistance of the element is approximately 53 ohms, and the element is made from wire that has a radius of 0.137 millimeters and a resistivity of 4.9 times 10 to the minus 7 ohm meters. Calculate the length of the wire needed for the element. So pause the video now, then unpause the video when you want to go through your answers. Right, how can we do this one? Well, in this first question, we need to work out R. We're given a power and we're given a potential difference, or an EMF. So therefore we can do the equation P is equal to V squared over R, an equation given to you in your equation booklet. The only trick here is that power is going to be 1000, not 1, because we don't work in kilowatts. So we work it through and we rearrange to work out R, which is 52.9 ohms. Now the next question, we've got resistivity. So we should be using the resistivity equation, and that is rho is equal to RA over L. Now the trick is here, we're given a radius and we've got to convert it into an area. So our area is going to be pi r squared. Now again, we don't work in millimeters, we work in meters. So you're going to have to convert your 0.137 millimeters into meters. You can then work out your area. You've got your length. Okay, so you need to work out your length, and you've got your resistance. So what you can do is rearrange the equation, make L the subject, plug the values in, and you get your answer worked out. The next question says a student builds a circuit that uses a filament lamp to heat a tank for reptiles. The circuit includes components that are designed to control the temperature of the tank. A thermistor and the lamp are positioned inside the tank. Figure 6 shows the circuit. The battery has a negligible internal resistance. Figure A shows the variation of R with the temperature T for the thermistor, and figure B shows the variation for potential difference with current for the lamp. So the initial temperature in the tank is 20 degrees Celsius, switch S is closed, and the potential difference across the lamp is 3 volts, so that the resistance of the parallel combination of the thermistor and the lamp immediately after S is closed is approximately 2.7 ohms. Determine the resistance of the variable resistor, and then determine the power of the lamp immediately after the S is closed. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, it's important that you've got to use data from figure 7. So what you'd note is, because the temperature is 20 degrees, you know that the thermistor resistance from looking at figure 7 is going to be about 11 ohms. So you look across, it says 20 degrees, so it's at 11 ohms. Now you can then also work out the resistance of the lamp from figure B, because we can say that resistance is equal to potential difference over current. So what we can then say is that we can work it out by saying, let's do the value of 3 volts over 0.85, because you're looking at your value for current and your value for resistance. So what we've got is our resistance of our thermistor, which is at about 11 ohms, and the resistance of the lamp, which is about 3.75 ohms. What we can then say is, because if we look at the circuit, we can see that the thermistor and the lamp are in parallel with each other. So you've got to use the parallel resistor equation, which is the 1 over R total equals 1 over R1 plus 1 over R2. So 1 over R total equals 1 over 11 plus 1 over 3.75. You work it through and you get your answer to be about 2.7 ohms. Now, it then says determine the resistance of the variable resistor. Well, you've got to use the concept now of potential dividers. So what you would say is, you know the potential divider equation is going to be that V out is equal to V in times by R1 over R1 plus R2. So what you would then do is you could use this equation to then work out your value, working it out. Now, another thing you could do by saying this is as follows. What you could say is, you could say that if you look at how they split with each other, you'll notice that it's a 3-to-1 split. So what you can do is multiply your previous answer by 3. Now the last one, it says determine the power of the lamp immediately after the switch is closed. Now this is quite a nice one, because what we now have is we have the potential difference in going through the lamp when the switch is closed. We've got the current from the previous question as well, so we can say P equals VI to get our answer out to be 2.5, 2.6 watts. The next question says as follows. So if we look on this one, it says suggest how the resistance of the parallel combination of the lamp of a thermistor and the lamp is likely to change in the period immediately after S is closed. On another occasion, the initial temperature in the tank is again 20 degrees Celsius. This time the resistance of the variable resistor in figure 6 is increased before S is closed. State and explain the effect of this change on the initial rate of temperature increase in the tank. So pause the video now, then unpause the video when you want to go through your answers. Right, so how will the resistance of the parallel combination change when S is closed? Well, it's the idea that the resistance of the lamp will increase whilst the resistance of the thermistor will decrease, because when the switch is closed, when S is closed, a current will flow through the circuit. So when the current flows through the circuit, it heats up both the thermistor and the lamp, but because a thermistor, when the temperature goes up, the resistance goes down, and for a lamp, when the temperature goes up, the resistance goes up. So you can make an idea regarding that, and then talk about how this links to the resistance of the combination. And your argument would be that you would think approximately, okay, that the idea is you don't know which one will dominate, but one's going to go up, one's going to go down, so it might stay the same or it might change slightly because of the fact of this variance. Now the next question says, state and explain the effect of the change on the initial rated temperature increase in the tank. Now the important thing to note is the initial temperature of the tank again is 20 degrees, and the resistance, the variable resistance, increase before S is closed. So this means that the initial rate of temperature will be lower because the potential difference across the lamp is reduced, so therefore it won't go up as quickly. Now why will the potential difference across the lamp reduce? Well, it's because the resistance of the thermistor is higher, and when we've got a situation like this in the potential divider situation, okay, you'll get more of the resistance going to the one with the more potential difference. When the potential difference increases, that will take more of the potential difference, so there's only a fixed amount from the battery, so therefore if more is being taken by the variable resistor, well then less is being taken by the lamp. So that tells us that the temperature will be lower, the temperature increase will be lower because the lamp is getting less, so therefore the power in the lamp has reduced. Now the next question says, the question is about the initial motion of a boat and a trailer when pulled up a ramp as shown in figure 8. The boat and the trailer are pulled by a motor which is connected to a 24-volt battery of negligible internal resistance. The motor is switched on at time t equals 0, and figure 9 shows how the current in the motor circuit varies with time. Determine how the total input of a 24-volt battery to the motor in the first 20 milliseconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, there are two methods to doing this. You'll notice that you got a current against time graph. So what you could do is if you work this particular idea through, say you do your current against time graph, the area under you can determine the area under the curve, okay, and what you can then say is you can then multiply, okay, the total area, which is going to be the charge because it's a current times by it's going to be current times by time because it's the area of a current time graph. So therefore you then multiply your total area, your charge, by 24 to get out your energy with our equation. Energy is equal to charge, the area under the graph, okay, times by the potential difference, 24. Another way you could do it is try to determine the average current. So you would say that over the first 200 milliseconds you could work out the average current by looking at the values on the graph. Then you can say E is equal to potential difference times by current times by time. You've got your values there, and you can work out once again to be 240 joules. Now the next question says the boat and trailer are initially at rest. In the first 200 milliseconds, the boat and trailer are raised to a vertical height of 3.3 times 10 to the minus 2 meters, and the speed is increased to 0.85 meters per second. Assume that all the useful energy output by the motor is transferred into kinetic energy and gravitational potential energy of the boat and the trailer. The boat and the trailer have a total mass of 180 kilograms. Determine the efficiency of the motor during these first 200 milliseconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you work it through? So firstly, work out the gain in kinetic energy. So you would do the idea of increasing speed is to 0.85 meters per second, and it's initially at rest, so it's a change of 0.85. So you do a half times by mass, which is given to you in the questions 180, times by velocity squared 0.85. Then you work out your potential energy by doing mass times by gravity times by change in height. We've got our mass as 180, we know gravity to be 9.81, and we know our change of height to be 3.3 times 10 to the minus 2. So we can work out our two values as kinetic energy is 65 joules and our potential energy as 58.3 joules. So you can work out efficiency by doing the total output is 65 plus 58, and then you can have your useful output energy that you want, and then you can work it through to be 51% or 0.51%. The next question says, either of the circuits shown in figure 10a and figure 10b could be used to reduce the initial current surge. So the thermistor and the fixed resistor have the same resistance where they are at the temperature of the surroundings. When the surge has ended, the boat and trailer continue to move at a constant speed to the top of the ramp. Explain, with reference to the properties of the thermistor and the fixed resistor, why the thermistor is preferable to using the fixed resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? So it's important that you compare and you contrast your thermistor with your fixed resistor. So you would say that heating will occur when a current passes through, because we know when a current passes through a wire or a component, there is a heating effect. Now the important thing to know is, what are the properties of a thermistor? Well, when the temperature of the thermistor goes up, the resistance goes down. So you would say that with less resistance, there's going to be less energy dissipated to the surroundings, so therefore there is less wasted power. Or you could indicate that there's more PD dropped across the motor, so there's less wasted voltage. You say there's less lost volts. But it's important to note that with a fixed resistor, you're going to get a fixed potential difference, so therefore a fixed amount of energy being released to the surroundings as waste. Here, because our resistance can change with temperature, we know that if the temperature goes up, the resistance goes down, so there's less energy dissipated to the surroundings, making it more efficient. Now let's finally look at some questions on periodic motion. Pendulums are used to make some clocks keep the correct time. Figure 13 shows a clock with a pendulum. The pendulum is made from a rigid bar of negligible mass with a large mass near the lower end. Assume that the pendulum behaves as a simple pendulum with a length equal to distance L between the point of suspension and the center of mass of the pendulum. The pendulum must oscillate with a time period of 1.400 seconds for the clock to keep correct time. The pendulum oscillates with a period of 1.402 seconds. Calculate the error in the time measured by the clock in 24 hours. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, it's the idea of, well, what is the difference between the ideal and the one you're actually given? And the difference is 0.002 seconds, because 1.402 is the value you got. You want it to be 1.400, so it's out by 0.002 seconds. So what you can then do is you can work out, okay, how many values that you are doing. So what you would do is you say 24 times by 60 times by 60, because that's how long it is a day, divided by 1.4, because you'll notice that in theory there should be that many time periods, because you're dividing it by 1.4, so you've worked out the number of seconds in the day, divided by 1.4, then multiplying it by the difference, which is 0.002, and it equals 123 seconds. Another way you could do it is just find the actual number of oscillations in 24 hours, like we said before, then find the necessary number of oscillations in 24 hours, then you will find the difference between the two, which is 88, multiplied by 1.4, which is how many you should have, and you get 123 seconds. Right, the next question says, show that the length is approximately 0.5 meters. Then the owner of the clock wants to make the clock more accurate by attaching a small additional mass to the pendulum. Explain where the owner should attach the small additional mass. And then the clock is moved to a warmer room, cause the rigid bar to increase in length. Explain how the owner must move the small additional mass in order for the clock to keep accurate time. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is asking to work out L. Now you should know, for a simple pendulum, T is equal to 2 pi times by the square root of L over G. That is an equation given to you in your equation booklet. So you can say T equals 2 pi square root L over G, pop your numbers in, G equals equals 9.81, so you get your answer to be 0.49 meters. Now the next question is asking where you should place the additional mass. Now the idea is the additional mass should be placed above the existing center of mass, because when you put your additional mass there, your new center of mass will now be nearer the point of suspension, so that would mean your effective length of the pendulum is smaller. So as a result, it'll be more accurate, because it wanted to be more accurate by going from 1.402 to 1.400, so you want a shorter time period, which is achieved by having a shorter length of the pendulum. Now the next question says, how must the owner move the small additional mass in order for the clock to keep accurate time if the rigid bar has increased in length? Well, the additional mass needs to be placed even higher because now we've got a longer bar, so we need to have a shorter effective length. The next question says the seat of a bicycle is attached to the main body of the bicycle by a single vertical spring. The spring has a spring constant of 7.2 times 10 to the 4 newtons per meter. The mass of the rider is 68 kilograms. Assume the weight of the rider is fully supported by the spring and that the mass of the seat is negligible. Show that the time period for free oscillations of the seat is approximately 0.2 seconds when the rider is sitting on it. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, what do you want to do? They're oscillating up and down. It's a spring. We look on our equation sheet. T equals 2 pi times by the square root of m over k. You've got m in the question, 68. You've got k, 7.2 times 10 to the 4. You know what 2 pi is, so you can work it through, and it's 0.19 seconds. Now, figure 10 shows the bicycle and rider approaching a series of speed bumps that are equally spaced. When the bicycle travels over the speed bumps at a certain speed, the rider experiences large amplitude vertical oscillations. Identify and explain the effect that causes the large amplitude oscillations. Then the rider experiences large amplitude oscillations when the bicycle travels at 5.8 meters per second. Calculate the distance between the adjacent speed bumps. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is this particular idea? Well, this idea is resonance. So large amplitude oscillations are caused when it is oscillating at resonance. So when do you get resonance occurring? Well, you get resonance occurring when the driving force or the driving frequency of the force is equal to the natural frequency of the object. So it's important to note that you've got to say in the question what's causing this driving frequency, this driving force, and it's the bicycle going over the speed bumps. That's causing a periodic force on your object, so that will cause a driving frequency, and that equals the natural frequency of the bike. You will get resonance. Now the next question says calculate the distance between the speed bumps. Now here you've got a speed, so what you can say is distance is equal to speed times by time. Now you've got to recognize that the time is going to be the natural frequency of your system. So what you can do is it's the same time period you worked out in the first question, because that is the time period of the natural frequency, okay, linked in there of this particular system. So what you can say is this time period is our natural time period, so you can say distance equals speed times by time. We've got speed, we had time in the previous question, we get 1.1 meters. Let's have a look at our next question. A student determines the period t of the oscillations for a mass spring system by measuring 10 oscillations of the system. The measurements were repeated. So table 1 shows these measurements. Calculate the mean value for t, then calculate the percentage uncertainty in your mean value for t. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, what you need to do is you need to add up all your values and divide by the number you've added up by to work out your mean. So you work that through, and then what you need to do is you then need to divide it by 10, because remember the table is showing 10t. So to show 1t, you get your average value for 10t and you divide by 10 to get 1.27 seconds. Now the next question is asking to work out the percentage uncertainty in your mean value. So how you do that is as follows. You've got to firstly work out your absolute uncertainty. Now when you do repeats, the way in which you work out your absolute uncertainty is by doing range over 2. So what you would do is you would get your range, you would then divide it by 2. Now again, remember that is for 10t, so you then divide that by 10 to find out the absolute uncertainty for t. You would then take your value for absolute uncertainty divided by this previous value, which is worked out the mean value for t, and times it by 100, and you get 0.8%. Now the next question says the mass on the spring was 0.400 plus or minus 0.008. So calculate the spring constant k. Then calculate the percentage uncertainty in your answer for k. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you work out this particular question? So what you've got to remember is, okay, that we say that t is equal to 2 pi times by the square root of m over k. You've got your value for m in this question, 0.400. In the previous question, you worked out your value for t. So what you can do is you can substitute them into the equation and then rearrange it to make k the subject. And what you can then do is work out your value, okay, and then work it out to be about 9.8 newtons per meter. Now the next one, calculate the percentage uncertainty in your answer. Now because we know that we'll have the values of, we'll say t equals 2 pi times by the square root of m over k. So when we rearrange that and we work out m, so we work out m to be the subject, what we can say is that we're going to have our equation, okay, of being, okay, linking the two concepts together, okay, you would have to say that m is going to equal k times by t squared times by 4 times by pi squared. Now obviously 4 and pi squared are irrelevant in working out uncertainties because they're constants. So you know that k is just a single value there, and you've got t squared and they're being multiplied together, so you've got to add your percentage uncertainties. Now because t is being squared, you've got to times your percentage uncertainty by 2. So what you would do is you would say that your value is going to, in m, is going to be equal to the percentage uncertainty of k plus 2 times the percentage uncertainty of t. Now you worked out the percentage uncertainty of t in the previous question. Now to work out the percentage uncertainty, okay, in m, what you would do is you would do 0.008 divided by 0.400, and you can work it through like that. Now also as well, sorry there, when I worked it out, I put m to be the subject. In fact, it would be k as the subject, my apologies. It would just mean there will be m over t squared, and once again when you divide two numbers together, you add the percentage uncertainties to work out the overall percentage of the value. So again, you're still adding them, okay, so you'd add your percentage uncertainty of m, add your percentage uncertainty of t, which is double because it's t squared, and you get your answer to be 3.6%. Let's have a look at our next question. So to investigate dampening in a system, the amplitude A of the oscillations was measured until a total of 50 oscillations were completed. Figure 11 shows the variation of amplitude with time. The dampening in the mass spring system causes the amplitude to decrease. The time taken for the amplitude of the system to decrease by half is constant and is called the half-life. So determine a reliable value for the half-life of this system. So pause the video now, then unpause the video when you want to go through your answer. Right, now it's important to note in this question it says select a reliable value. So how do you get a reliable value? Well, you work out your half-life by getting two values on your graph where one is half the other. So for example 4 and 2, 3 and 1.5, and you would go down, you would read the value for time for both values, and the difference between the two is going to be the half-life. But to gain a reliable value, you need to be doing at least this process 3 times and averaging the result. So you might want to do 4 and 2, 3 and 1.5, 2 and 1. Work out your values for all those different half-ends and then average them out, and you get your average value for the half-life for the system. Remember, to get a reliable value for a half-life, you've got to do it about 3 times at least to remove any effects of randomness. So you should be getting an answer in the order of 23 to 26 seconds. So I hope you've enjoyed and you found this revision session useful. So in this revision session, if we've been successful and learned today, we should be able to answer A-level physics examination style questions, assess our understanding of A-level physics, and understand what topics we need to improve upon for A-level physics. Thank you very much for watching this revision session on Paper 1 topics for AQA A-level physics on the 2022 examination topics. Thank you very much for watching and have a lovely day.